Okay, now we like to discuss the glue velocity and the chromatic dispersion. Here we consider a pulse containing varying frequencies. For such pulse, we can express it in this way. In this expression, you can see that here is the plane waveform, and for different value of k, we can find out the corresponding omega. And for each component, each kind of plane wave, they have their own amplitude here. As a result, this integral shows the summation of different plane wave, which corresponds to different value of k. So this is the summation of different components of different frequencies. Okay, and now this is the general expression for the E field. Here we consider as t is 0. As t is 0, then we take this value into this expression. We will have E of z 0 will be integral from minus infinity to positive infinity a of k times exponential minus jkz dk. So this expression represents the E field as t is 0. That is, this is so-called initial field. And clearly, the initial field is the field input as t is 0, right? And now we suppose that although this pulse contains different frequencies, but if we consider the frequency distribution of this pulse, suppose that most of the frequency are focused at omega 0. So the frequency curve will be plotted like this. Most component is focused on the omega 0 here. So we suppose that the pulse is sharply focused on omega 0. So omega 0 component has a large amplitude. For other frequency component, they have smaller amplitude. Okay? As a result, as I have said, since omega 0 component has a large amplitude, so we can say if you plug the function of a of k, it will show sharply on K0, like this curve. This curve is we plot the A of K, and from the black curve you can see that at K0 we have the largest value of A of K, and for the other K value we have smaller value of A, smaller value of the amplitude. Since the A of K and the omega K, they all focus on K0 and omega 0 respectively, then we can use the Fourier expansion to expand omega K. We expand omega K around omega 0 because it is sharply focused at omega 0 in the following way. Due to omega of K is sharply focused at omega 0, so we can ignore the higher order term here. Okay, as a result, omega of K can be approximately expressed in this way, and we will take this expression into the E field we have right here. After we obtain the expansion of omega K, we can take it into the E of t like this. Okay, and you can see that we obtain a very long expression for the E of t with a very complicated integral shown here. Then we try to simplify this integral, so we define a parameter psi equals to z minus d omega over dk times t. As we have defined the parameter psi here, the long integral can be regarded as a capital V function of psi. Then the above E function can be expressed in a very simple way like this. It looks like a V function propagated to the Z direction like a plane wave. Okay, so here is the plot of the E function. As t is 0, we have the pulse shown here. As time increased, the pulse will move to the positive z direction. Then our purpose is that we want to find out the velocity of this pulse. And let us write the v function in a detailed way. Okay, how to find the velocity of the pulse? We try to focus on a specified point and to observe that how this point moves as time increased. To find out the velocity, we focus on a specified point. So suppose that the specified point we focused on has the c value of c1. At time is t, the specified point will at the position of z. As time goes to t plus delta t, the specified point will move to z plus delta z. Since these 2 points are the same value of c1, we can express it as this. Okay, and the first expression means at t and position z, and the second is the condition at the situation as t is t plus delta t, position is z plus delta z. Both these two situations corresponds to the value of c is equal to c1, so they are equal to each other. And from this equation, we can derive the corresponding velocity of this pulse. We call it groove velocity because it contains components of different frequencies. And the groove velocity then can be deduced as delta z over delta t. Okay, and from the above equation, you can know that the delta z over delta t can be obtained as d omega over dk. And this one is so-called groove velocity. And now let us perform some summation here. And we have learned the velocity of the phase is Vp, which can be obtained by omega over k. And the velocity of the of different components of different frequencies, that is groove velocity. And this one can be calculated as d omega over dk. So please remember how to find out these two velocities. Due to the wave number k can also be expressed like this. Then we can know that dk can be deduced as omega dn plus n times d omega over c. Then we take the common term out here, And we then have omega dn of d omega, omega times dn over d omega plus n inside here. And then we can re-express the phase velocity, which is defined as omega over k in this way, c over n, which the n value is a function of omega. And n I have mentioned before that n is the index of the material. Besides, we can rewrite the glue velocity. Initially, the glue velocity is defined as d omega over dk. And we now have it re-express the dk here and take the result back into here. Then we can have Vg is equal to c over n plus omega dn over d omega. And also we can re-express the glue velocity in terms of wavelengths like this. C over n minus lambda times dn over d lambda. So if you know the relationship of index with omega or the relationship of index with lambda, then you can obtain the glue velocity in this equation, from these equations. From the previous slide, we have learned that the glue velocity depends on the wavelength, right? And you can also say that the glue velocity depends on the frequency. So we can say that EM wave with different frequency. They have different glue velocity. This phenomenon will cause a very severe problem in optical communication systems. For example, if we have EM wave of different frequencies, they start at the same point. And if they want to propagate at a fixed distance, and due to they have different velocity, then they will arrive the final point at a different time. Okay, and this means that different EM wave of different frequencies, they will arrive the final point at a different time, and then we will have so-called glue velocity dispersion. For example, we may have signals of F1, F2, and F3. They all start at the same point, and we want they to propagate to a fixed distance to the final point here. Due to these three signals, they have different frequencies. That is, they have different glue velocities. As a result, a signal F1 arrives the final point. Signal F2 may not arrive the final point, and signal F3 may have already arrived the final point like this. Okay, and this phenomenon is so-called glue velocity dispersion, which is caused by that signals of different frequencies have different glue velocity. And such effect will result in so-called pulse burden in optical communication systems. The below figure shows the problem caused by the pulse broadening in optical communication system. For example, we input the pulse train like this into an optical communication system, and you can see that the pulse train carries signals of 1, 1, 1, 0, 1, 1, right? And after these pulse signals propagates along about 20 kilometers. Due to the group velocity dispersion, the pulse will broaden like this. Okay, each pulse will broaden like this, and you can still tell the signal by the pulse. They could be 1, 1, 1, 0, 1, 1, right? But however, if the pulse train propagates along the distance about 50 kilometers, each pulse will broaden like this. Very severe problem. And you can see that each pulse they overlap very much. As a result, the final signal will look like the black solid line here. And from the black solid line, it is very hard, very difficult for you to tell that which is 1 and which is 0. You cannot clearly tell that how many bits in these signals, right? Besides, for the position where should be 0, due to the overlap, the field here is normal 0. They may be very high, which will make the detector to feel that this bit corresponding to the value of 1, and this is so-called error bit. So the pulse broadening caused by the group velocity dispersion will result in error bit in our communication system. So the group velocity dispersion is not what we want in the optical communication system.